High-speed communication is a critical part of modern computing systems. Today we do it electrically, but it's becoming more and more difficult. Tomorrow we want to do it optically. At Intel we've known that optical communications has many advantages. You can go faster, you can go farther, you can do it without electromagnetic interference.
We know that the computer clock speed runs at gigahertz. Everybody knows that. But you can't get information in and out of the computer at high speed, high capacity, where it's cost effective. It would be great if you could.
Optical communication has been very expensive. The optical components are 10, 100 times more expensive than their electrical equivalents. We thought if we could apply our silicon technology to photonics, we could achieve all the advantages inherent in photonics without the costs of today's photonic hardware.
Well, you know, we started a silicon photonics program a number of years ago, and the vision was pretty simple. We have great expertise in the use of silicon in building very complex chips. Silicon has never been used much as a medium for building optical parts, and we thought we could change that we could begin to use silicon, a very cheap and cost-effective medium, to make breakthroughs in the optical domain, even though most people at that time really didn't think that was possible.
What we've done to create this hybrid silicon lasers, we've partnered with the University of California at Santa Barbara and taken indium phosphide and the light emitting capabilities of indium phosphide and married that with silicon and silicon photonics capability that we have at Intel. And by combining the best of these both two materials together, they've created a hybrid silicon laser.
The hybrid silicon laser has several unique characteristics. Firstly, it produces a low-cost solution to a laser in silicon. It's electrically pumped, and it combines the advantages of both 3.5s and silicon technology.
This allows us to take the similar analogy of the vacuum tube to the transistor, to take all these optical components, integrate them onto silicon, and create a whole new optical communication technology on a single silicon platform.
Now we can envision systems that are completely different, whereby because of the cost being smaller, that you can put optical transceivers where you never thought they could be put before.
We're looking at backplanes, we're looking at new ways of doing data center communications between chips, around chips.
There are only a certain few times in the history of the community where revolutions really occurred. One of them was when low-loss optical fiber was invented. Another one was when the semiconductor laser was made to operate at room temperature and at high enough CW, which means constant power. Another one was when the optical amplifier was invented, which allowed you to go thousands of kilometers without having to detect and retransmit. We're about to have that same revolution when you think of silicon photonics.